modulus. Thomas Young demonstrated experimentally that magnitude of strain produced is the same for the stress being tensile or compressive. The ratio of stress sigma to the longitudinal strain epsilon is thus defined as Young's modulus. Young's modulus is represented by y. Y equals sigma by epsilon. This can be written as y equals F by A by delta L by L, which equals F into L by A into delta L. Strain is a dimensionless quantity, and hence the unit of Young's modulus is the same as that of stress, that is, Pascal. Metals usually have a large value of Young's modulus. This can be seen from the table given. This is the reason why most heavy-duty applications make use of metals. Determination of Young's modulus for the material of a wire. In the last section, we defined the meaning and relevance of Young's modulus. Let us now learn how to experimentally determine Young's modulus. We take two wires, A and B. Both these wires are made of the same material, have the same cross-sectional area, and have the same length. The wire A carries on it a millimeter scale and is known as the control wire or the reference wire. It also carries at its end a known weight, which is used to keep the wire taut. Wire B is known as the experimental wire. It is attached to a vernier scale, which rests next to the millimeter scale, and has provision at its end to add weights. Adding weights to the experimental wire causes it to stretch under the downwards acting force of the weights. The reference wire compensates for any changes in the length of the wire due to temperature changes, since both wired would be equally affected. Initially, after the wires are loaded, the vernier reading is noted. The experimental wire is then loaded with more weights, leading to tensile stress in the wire. The vernier reading is then noted again. Weights are then added again to the experimental wire, adding to the stress, after which vernier reading are noted again. Elongation of the wire is given by the difference in the vernier readings as weights are added. Let the initial radius of the wire be r, and the initial length of the experimental wire be L. The area of cross-section of the wire, thus, is pi r square. Let delta L be the elongation produced in the wire due to the mass m. The force applied on the wire equals mg, where g is the acceleration due to gravity. The Young's modulus of the wire B is then given by y equals sigma by epsilon equals mg by pi r square into L by delta L, which equals mg into L by pi r square into delta L. Shear modulus. Shear modulus of a material is the ratio of the shearing stress to shearing strain of the material. Shear modulus is represented by G. It is also known as the modulus of rigidity. G equals shearing stress by shearing strain, which equals F by A by delta X by L, which equals F into L by A into delta X.
We know that shearing strain is equal to tan theta equals theta.
Therefore, G equals F by A by theta, which is equal to F by A into theta.
The shearing stress sigma S can also be expressed as sigma S equals G into theta.
Shear modulus has the SI unit Newton per square meter, or Pascal. For most materials, the shear modulus G is almost equal to Y by 3. The table here shows the shear modulus for some common materials. Bulk modulus. We studied in earlier sections how submerging a body in fluid leads to it experiencing hydraulic stress. Hydraulic stress leads to a decrease in the volume of the body and also leads to strain, which is known as volume strain. Bulk modulus is the ratio of hydraulic stress to the corresponding hydraulic strain. Bulk modulus is represented by the symbol B. B is equal to minus P whole divided by delta V by V. The negative sign indicates that as pressure increases, the volume decreases. Thus, when P is positive, delta V has a negative value. For a system in equilibrium, bulk modulus B always has a positive value. The SI unit of bulk modulus is the same as that of pressure, N per meter square or Pascal. The table here shows the bulk modulus of some common material. Compressibility, K, is the reciprocal of bulk modulus. Compressibility is defined as the fractional change in volume per unit change in pressure. K is equal to 1 by B, which is equal to minus 1 by delta P into delta V by V. From the table for bulk moduli, it is clear that the bulk moduli for solids is much larger than that for liquids, which is again much larger than that of gases. This means that solids are the least compressible of all materials, while gases are the most compressible. In fact, gases are about 1,000,000 times more compressible than solids. Solids are incompressible by virtue of their tight molecular structure. Liquids are more loosely bound, which gives them a degree of compressibility, while gases are the least tightly bound, making them extremely compressible.